Hey there, my name is Annika. Welcome to Chapter 10 of Physics, which is Thermodynamics. This chapter is broken down into 3 segments. The first is relationships between heat and work, and then later on we'll be looking at the first and second laws of thermodynamics. Let's start with relationships between heat and work. As I sort of introduced in the last chapter, heat, work, and internal energy are all related. Internal energy increases through an increase in work, and then that in turn leads to an increase in temperature. For example, if you warm your hands on a cold day by rubbing them together, that friction produces internal energy, which heats your hands. In the same way that internal energy can increase through work, it can also decrease through a loss of energy as heat. Alternatively, energy as heat can be transferred to a substance, and then that energy is lost when it's used to do work. And heat and work are similar in that both describe energy transfer. In other words, an object does not have heat or work, but rather both work to increase its internal energy. When we're looking at thermodynamics, there are 2 main contexts to consider. The first is the system, like this test tube I've drawn here. This is simply the group of all of the objects that you are studying specifically for an experiment or problem. Then beyond the system, there's the environment. These are the surrounding conditions of the system, and those can also influence the system. In thermodynamics, work is defined in terms of changes in pressure and volume. So we have these equations for pressure and volume. Pressure is expressed as F, which is force, divided by A, which is area. And the units of pressure are the Pascal, which is written as a capital P and a lowercase a. That will come in handy for problems later on. The change in volume is expressed as area, just like in the pressure equation, times a distance. So if we multiply the pressure times the change in volume, we end up with force over area times distance. As you can probably tell, the 2 areas will cancel out, leaving us with force times distance, which is work. And a note, work is only done if volume changes under constant pressure. So it accounts for this delta V, but the pressure must stay the same. Now that I've introduced the idea of energy transfer through heat and work, we're going to look at 3 thermodynamic processes. And just to note, these processes are very idealized. They rarely happen in the real world exactly as they will be described. But for the sake of making these calculations more simple, we're going to neglect either heat or work in each type of process. The first type of thermodynamic process is isovolumetric. This is a process in which volume remains constant and no work is done. The example that the textbook gives for this process is a bomb calorimeter. This means there's a calorimeter similar to the ones I discussed in Chapter 9, where there's a chamber of water inside that's used to test a substance in some way. And then inside the calorimeter, a bomb goes off. Because the bomb is inside such an enclosed container, the volume must remain constant because it has no room to expand. In isothermal processes, the temperature remains constant and the internal energy is unchanged. So in other words, there's no change in temperature or internal energy. These processes must happen slowly in order to keep the temperature constant. For this process, the book gives an example of a balloon, which is inside a building when a storm is coming, and the changes in pressure cause changes in the size of the balloon. This is slightly hard to visualize in real life because it's not an example that takes place very frequently. But another type of process you can think of as being isothermal is phase change. As we saw in the last chapter when I drew the graph, which plateaued at places where there were changes in phase, there is no temperature change while an object is changing phase, therefore it's isothermal. The final type of thermodynamic process is known as adiabatic. This is a process in which no energy is transferred, or the net change in energy is 0. Unlike the isothermal process, this must happen rapidly. So an example of this kind of process is when a balloon is inflating. The internal energy of the gas in the tank decreases because of lower pressure, because it's expanding into more space as it fills the balloon. However, as this internal energy decreases, the work of the gas inflating the balloon cancels out this decrease because it's increasing the size of the balloon. Therefore, the 2 changes negate one another, and total energy is conserved. And once again, I'll emphasize that these situations almost never occur in real life exactly as they've been described here. They're just approximated using these ideal examples. Now we'll do some practice problems with thermodynamics. Number 1. Gas in a container is at a pressure of 160,000 pascals and a volume of 4 meters cubed. How much work is done by the gas if it expands at constant pressure to twice its initial volume? Okay, so we have our equation that I introduced where work equals pressure times the change in volume. We know that the pressure of the system is 160,000 pascals. Then we're looking for change in volume. Well, it starts out at 4 meters cubed, and then it says that it expands to twice its initial volume. That means that the gas ends up at 8 meters cubed, and its initial volume was 4 meters cubed. Now we can simplify this. We'll have work equals 160,000 times 4. And then if I multiply that out, I get that the work done by the gas is 6.4 times 10 to the 5th joules. Number 2. A balloon is inflated with helium at a constant pressure of 430,000 pascals. If the balloon grows from 0.00018 meters cubed to 0.00095 meters cubed, how much work does it do on the surrounding air during its expansion? So once again, we know that work is equal to pressure times the change in volume, and we're given the pressure, so work equals 430,000, and then we're multiplying by final volume minus initial volume. So if the final volume is 0.00095 meters cubed, the initial is 0.00018, then we're ready to solve by multiplying these together. So when I do the subtraction and then multiply, I get that the work that the balloon does on the surrounding air is 330 joules. Number 3. Steam does 0.84 joules of work on a piston within the cylinder of a steam engine at constant pressure. The diameter of the piston is 1.6 centimeters, and the piston travels 2.1 centimeters. What is the pressure of the steam? So first of all, we know that we have 0.84 joules of work, and that work will be equal to pressure times the change in volume. Now, to find the volume change of the cylinder, we first have to convert the units. So we know that this height is 2.1 centimeters, which is 0.021 meters. And we know that the diameter of the cylinder is 1.6 centimeters. So its radius will be 0.8 centimeters, or 0.008 meters. Now we're ready to solve for the change in volume. So we have 0.84 equals the pressure is what we're trying to find. And then we have the volume of the cylinder. So the change in volume is going to be the amount that the volume decreases when it's pushed in 2.1 centimeters. So I'll write in the equation for the volume of the cylinder. That's pi r squared times h. And then if I plug in the actual numbers we have, that's pressure times pi, r is 0.008, so that's squared, times h, which is 0.021. Simplify that a little bit, and I get that 0.84 equals 4.22 times 10 to the negative 6th times p, which is the pressure that we're solving for. Then finally, if I divide both sides by 4.22 times 10 to the negative 6th, I get that the pressure must be equal to 1.99 times 10 to the 5th pascals.